This video is for section 3.1, using and expressing measurements. The learning goal is to understand accuracy and precision. So let's take some notes about that goal. First, some vocabulary. In chemistry, the accuracy of a measurement is a measure of how close a measurement is to the true value. The precision of a measurement is a measure of how close repeated measurements are to each other. An error in measurement is a measure of how inaccurate a measure is. Here's the mathematical formula for finding error. Take the experimental value and subtract the true value. That means when you are doing an experiment and you make a measurement, take your value and subtract the actual true value. To determine if a measurement error is large enough to be serious, we can find percent error. This is a comparison of the amount of error to the true value. And here's the mathematical formula. Take the absolute value of the amount of the error, divide by the true value, and then multiply by 100 to change to a percent. Here's a check for understanding question about finding how much error is made and finding what the percent error is. Please use those two math formulas to answer this check for understanding question. I'll pause the video for you to work on this, and then we'll discuss it before we get back to the video. Here are the answers to that first check for understanding question. The amount of measurement error was 0.10 grams. That's how much different your measurement is than the correct value. Now, is that a large amount of error or an acceptable amount of error? When you take the absolute value of that number, it's still positive 0.10, and compare it to what the true value should be, you find out that it's only a 0.29% error, less than a 1% error. You and your partner measured very well. There are two more check for understanding questions. I'll pause the video for you to answer these, then we'll briefly discuss and get back to the video lesson. Moving on, a key concept in chemistry is that when you perform calculations with measurements, you must give the answer so that it shows the correct amount of precision based on the measuring devices that were used. When a chemistry calculation involves adding measurements together, here's what you need to think about. The answer to an addition calculation should be rounded to the same number of decimal places as the measurement with the least number of decimal places. Let's discuss this example to make sense of that. You mix 3 samples of liquid, and here are the 3 amounts. The first is 5.60 milliliters, next 11.3 milliliters, and last 180.759 milliliters. How much liquid is there in total? Well, we know we want to add these numbers together. But notice that these measurements go to different decimal places. The first is measured to the hundredths position. This is measured to the tenths position. And this last one is to the thousandths position. These samples of liquid must have been obtained with different measuring devices, capable of different amounts of precision. This one here with 1 decimal place had the least amount of precision. There must have been the fewest marks on that device. This one here that goes to the thousandths position had the greatest precision. That had the most marks on that measuring device, allowing for more precise measuring. When we add these values together, we need to round our answer so that it has only 1 decimal place, because this one here had only 1 decimal place. Take a calculator, add these 3 numbers together, and then round it off so it only goes to the 10th position. I'll pause the video for you to do that. Write your answer in this spot right here. The correct answer is 197.7 milliliters. The calculator screen says 197.659. But we can't report the final answer to that many decimal places. Doing that would misrepresent how precise our original measurement tools were. Remember that we had one measurement that was only precise to the 10th position. So we want to round our answer to the 10th position. Because the next number is 5 or higher, you round this up to a 7 and drop off the remaining digits. Next, let's look at the situation that involves multiplication or division of measurements. Here is the key idea. The answer to a multiplication or division calculation should be rounded to the same number of significant figures as the measurement with the least number of significant figures. When we discussed adding problems, the rule involved looking at decimal places. This time, the rule involves a concept called significant figures, and we'll discuss what that means. But before we do that, let's take a look at this example. The density of a substance is 1.32 grams per milliliter. We have 3.8 milliliters of the substance. What is the mass in grams? And here's the math formula that you use. So using this formula, we see we want to multiply the two numbers together. 1.32 times the 3.8. When you multiply the milliliters, we'll cancel away the unit milliliters, leaving the unit grams. We need to type this in the calculator, but then round the answer so it has the correct number of significant figures. This first number has 1, 2, 3 significant figures. This number here has 1, 2 significant figures. That has the least amount, so we want to round our final answer to have 2 significant figures. Please type this in and write your answer in this spot right here. The result is 5.0 grams. This number has 1, 2 significant figures. The calculator actually says 5.016, but that number has 4 significant figures, which is too many. If we were to write this value down, that would misrepresent the quality of the measuring devices that were used. You will have noticed that when rounding the answer to an adding problem, you look at the number of digits after the decimal point. But when rounding an answer to a multiplication, you're counting up digits that are called significant figures. So we need to discuss what significant figures are. The significant figures in any measurement are all of the digits that are known for certain plus one more digit that is estimated between the marks on the measuring device. The concept of significant figures only arises when numbers are measurements that were obtained from measuring devices. Let's look at a couple samples. Here's a beaker containing a blue solution. How many milliliters are in this beaker? We know for certain that the measurement is above the 200 line, but then we can estimate in between the marks. It's almost halfway between 200 and 250, so maybe it's 220 milliliters. The 200 we know for certain, and then we've estimated that additional 20 milliliters. Cool. Let's make believe that this drawing represents a graduated cylinder that's filled with water. Measure to the bottom of the meniscus. On your notes packet, jot down what measure you think this is. Okay, here's the answer. This long line going all the way across the tube is 35. And if this long line going all the way across is 40, then these marks in between must be counting by 1 milliliter. This one is 36, 37, 38, 39, and then we're to that line which is 40. We know for sure that the meniscus is above the 36. So our answer is 36 point, and then we're going to estimate one more digit. It appears to be exactly halfway between this mark and this mark, so I'm going to estimate a 5, and this would be in milliliters. 36.5 milliliters is the answer to this question. How'd you do? By the way, this number has 1, 2, 3 significant figures in it. We discussed the concept of significant figures by looking at actual measurement devices. Now let's talk about significant figures more theoretically and look at some rules involving significant figures. When you look at a measurement that's written and you want to know how many digits are significant, here are the rules you follow. First rule, all non-zero digits are significant. Second rule, zeros on the end of the number and after a decimal point are significant. Third rule, zeros that are in between non-zero numbers are significant. However, sometimes zeros are not significant. Let's take a look at that. Zeros at the beginning of a number are not significant. Zeros at the end of a number, if they aren't after a decimal point, are not significant. There are also two special cases in which written numbers have an unlimited number of significant figures. That's when the number is a count of objects instead of a measurement off a measurement device, or when the number is a defined conversion factor. For instance, there are 1,000 millimeters in 1 meter. If you're doing math with that 1,000, you're not restricted to giving an answer with only one significant figure, even though the number 1,000 has one significant figure. Because it's a conversion factor, it has an unlimited number of significant figures. Let's make sense of these rules by doing some practice problems. When we answer these, we need to refer back to our rules. Determine the number of significant figures in each measurement. Question A, 0.32 milligrams. It has 3 digits shown, but are all of them considered significant? Remember that all non-zero numbers are significant, so certainly this one and this one are, but what about the 0? This 0 comes at the beginning of the number. It is not significant. This number has 2 significant figures. Now question B. How many significant figures are in the number 120 milliliters? This has 2 significant figures. This 0 is at the end of the number, and it is not after a decimal point. Question C. How many significant figures does this number have? This has 5 significant figures. All non-zero numbers are significant, and zeros that come between non-zero numbers are also significant. Question D. How about this number which is written in scientific notation? This has 2 significant figures, the 2 and the 5. Question E. How about 11.000 feet? This has 5 significant figures. Zeros on the end of the number are significant as long as they're after a decimal point, because they indicate the level of precision of that measuring device. How about question F? What do you think? This one also has 5 significant figures. And now question G. What do you think on that? This has an unlimited number of significant figures because it's counting objects, toothpicks. It's not a measurement that came from a measuring device. The reason you need to know these rules is because whenever you do a multiplication or division problem in chemistry, you have to round your answer off based on significant figures. So you need to know how many significant figures are in the different measurements in the problem. Here are some check for understanding questions. Please evaluate them and correctly round the answers based upon the rules that are in your notes. I'll pause the video for a few minutes for you to work on these, then we'll discuss them and then get back to the video. Here are the solutions to the check for understanding questions. Question 1, 25 meters times 100 meters. This is a multiplication problem. When you round your answer, you need to think about significant figures. This first number has 2 significant figures. This measurement here has 1 significant figure because zeros on the right don't count unless they're after a decimal point. The final answer has to be rounded to have 1 significant figure. When you type it in, the answer on the calculator is 2,500 square meters. But that number has 2 significant figures. That's too many. So you need to round to 3,000 square meters. Question 2, 55.63 grams divided by 20.5 liters. This is a division problem, so when rounding you use the significant figure rules. This number has 4 significant figures, and this measurement has 3 significant figures. The final answer needs to be rounded to 3 significant figures. On the calculator, you get a number like 2.71365, and there's even more numbers, grams per liter. When you round to 3 digits, you get 2.71 grams per liter. Question 3. 20.005 centimeters plus 12.65 centimeters. This is an adding problem. This time, you don't have to worry about significant figures, but you do have to look at decimal places to the right of the dot. This has 3, this one has only 2. Your final answer can have only 2 numbers to the right of the dot. So on the calculator, you'll get 32.655 centimeters, but that has too many digits. You need to round to 32.66 centimeters. Now number 4, 4.2 times 10 to the third joules times 24.84 seconds. This is multiplication. This one uses the significant figure rounding. This first number has 2 significant figures. When you have scientific notation, you're only looking at the coefficient to get your significant figures. This number here has 4 significant figures. So we want our final answer to have 2 significant figures. But when you type this in the calculator, you get 104,328 joule seconds. How do you round this? Well, you can't round it to 1,0,0,0,0,0 because that only has 1 significant digit. And you can't round it to 1,050,000 because that has 3 significant digits. And it doesn't make sense to round this to 1,1,0,0,0,0 because what would be the reason you'd put a 1 here? That next digit's not 5 or bigger. That's why we use scientific notation. Because in scientific notation, we can make the coefficient have whatever number of significant figures we want. So we round this to 1.0 times 10 to the 5th. This has 2 significant figures. Failing to round answers to calculations almost always results in writing a value that has too many digits. This misrepresents the capabilities of the original measurement devices. Remember to think about the rounding rules for every math problem. This is the process you need to go through in your head this year. Are you doing an adding or subtracting problem or a multiplying and dividing problem? If you're doing adding or subtracting, pay attention to the decimal places, to the numbers to the right of the dot. If you're doing multiplying or dividing, then pay attention to significant figures. This concludes the video about measuring accurately and precisely and recording answers correctly by rounding them based upon the measurements involved in the calculation.